In seventh grade, as students are continuing to develop some fluencies around using formulas and using geometric formulas for finding different measurements, such as area or perimeter, one of the figures that they're introduced to for the first time and finding this measurement for the first time is circles. Most sequences in seventh grade, by the time students get to the area of circles, they've already done a few really important things in the progression to understand where the formula for area of a circle comes from. Just like with other shapes and other ideas, we don't want students to, if students are only using a formula but they don't understand where the formula comes from, that fluency isn't based on understanding, then it's not really fluency. And for students to understand truly the formula for area of a circle, they need a few understandings prior. And so I've got a circle here with a couple things that are important. In most sequences, by the time students get to area, they will have already talked about circumference and finding circumference, that relationship between circumference and diameter, and that for any circle, when we divide those two things, we get pi. That's where that ratio of pi comes from. They will be familiar with what the diameter of a circle is and also the radius of a circle. Now, when we get to area of circles, students also most likely have been dealing with some other figures as well in finding area. In sixth grade, they sort of formalize finding the area of rectangles and other parallelograms as well as triangles. In seventh grade, they formalize the idea of finding the area of trapezoids, even though in sixth grade they may do it thinking as composite figures, and in seventh grade we start out thinking of trapezoids, at least for finding their area, as composite figures. And all of those, the triangles, the trapezoids, the parallelograms, so many shapes, they're all based on the area of a rectangle. And then we get to circles, which is not a polygon, and we treat it differently. We stop making that connection back to rectangles when in fact the formula for area of a circle is based in that understanding for area of a rectangle and can be derived from the area of a rectangle. In fact, in seventh grade, one of the standards calls for students to explore that relationship and discover just that. So in this video, we're going to look at how we can help students understand how the area of a circle and its formula can be derived from a rectangle. So if we think back to triangles, trapezoids, other shapes, and how we can sort of turn them into rectangles to help understand how they're related to rectangles in order to find their areas, or going the other direction, we want to do that same thing with a circle. So if I take a circle and break it into lots and lots and lots of, I'll call them like pie pieces, right? Let's say I just broke it into 4 pieces. They're sort of triangular in nature, and I know that I can make a rectangle out of triangles. And so if I were to rearrange these pieces sort of like this, I get a shape that is not a rectangle, not a parallelogram, not a polygon, but it's getting there. It's more rectangular. It's more like a parallelogram than the circle. And if we're talking about area, I haven't changed the area. The space inside is the same. So what I might do now is break it apart even further. The problem with this is these sort of the round, I guess we call it the base. It's not the base, but this sort of round section on the circle. But if I make it smaller, I make it a little less round. And so now I might have a figure that looks something like this. I broke it into 8 pieces, so I'm going to put 4 on the bottom and then 4 on the top. And now I'm getting a figure that looks a little bit more like a parallelogram. And the idea here is if I could continue to break this circle into infinitely more and infinitely more and infinitely more pieces, if I could have an infinitesimally small pie piece, as I continue that process, these round edges are going to become more and more flat, more and more flat. These sides over here are going to become closer and closer and closer to a right angle. And then theoretically, if we did this an infinite number of times, we would end up with a perfect rectangle. And so now we've taken all of the area inside of a circle and we have turned it into a rectangle, which is great because I know how to find the area of a rectangle if I have the base and the height. So now all we need to do, if we know that area of a rectangle is the base times the height, is turn this back into a circle and figure out where those dimensions came from. When I think about the height of the rectangle, how is that represented in the circle? When I think about the base of the rectangle, how is that represented in the circle? So I'll start with the height. If we look back up to this image, we can more clearly see the height here and here. As we break this infinitely smaller and smaller and smaller and smaller, this distance here isn't changing. What's changing is sort of the round pieces of the circle. And so this isn't changing. So if we kind of trace this back to where it was in the circle, that was just the radius. And so the first thing that I'm going to do is rewrite this formula thinking, okay, area equals, not base, right? It's going to eventually be something else. But for now, I'm going to replace the height with the radius because I know that the radius, if I restructure this as a rectangle, the radius becomes the height of the rectangle. So now we have to figure out what the base comes from. And if we look back at the ones that look a little more circular, have those edges, we see that each side of this figure represents halfway around the circle. Here's sort of the bottom half of the circle, the top half of the circle. So back on the circle, this is the base. This distance becomes this distance, and then this distance becomes this distance. So we just have to think in terms of what we know about circles, what is that? And the distance around a circle is the circumference, so the base is just half of that. So now I can rewrite this again one more time, that the area is half of the circumference. The area is half of the circumference times the radius. So if we knew the circumference, we could find half of that, multiply it by the radius, and that would give me the area of the circle. Now I think we can make this a little more friendly because circumference is typically something we're not given. It's something we would have to calculate. So I want to break this down into things that all represent dimensions that we are commonly given, which is typically just either the diameter or the radius. And if we have one, it's pretty easy to figure out the other. So I know that circumference, because of this relationship, circumference is just pi times diameter, or sometimes it's written as pi times the radius times 2, because the radius, when you multiply it by 2, you get the diameter. So those are equivalent. So because I already have radius in the formula, I'm going to go ahead and go with this, this version of circumference. So area equals 1/2 of pi times the radius times 2 times the radius. And so now we're getting there. If you're familiar with the formula for area of a circle, this is starting to look very familiar to what you are used to seeing. Now I notice in this formula there's a 1/2 and a 2, and this is all multiplication. If I multiply 1/2 times 2, I'm going to get 1, and because of the identity property, when I multiply by 1, my values aren't going to be impacted. And so I'm going to rewrite this without the 1/2 and the 2, and say that area equals pi times the radius, which radius times radius, I can clean that up even further and say that area is pi times the radius squared. And there is our formula for the area of a circle, but derived from our understanding of rectangles.